Welcome back, class. So we were learning about the communication systems, and lastly we have learned about the basics. Then we moved to the power calculations in terms of dB. We learned about different kind of noises in the system, and then we learned about the noise factor calculation of a complete system. So we are moving towards the second chapter of this course, second part of this course, and here we are going to learn about the frequency domain analysis of the signals, okay, in the communication system, that how we can characterize the signals and systems in the frequency domain. Frequency domain analysis is basically the most efficient technique for the analysis of the signals. So before moving to the frequency domain analysis, we will review some basic concepts about the signals, basic terminology calculations, and then we will move to the frequency domain. So the first part, let's have a look at the brief about the signal and spectra. We will briefly review the DC value and RMS value of signals, how we can calculate them. dBm, we already know that, it will be a brief review again. The power of the signal, Fourier transform and spectra, what is this? What is the linear system and distortion, band limited signals and sampling, what is this and how we actually do the sampling, and discrete Fourier transform and bandwidth of signals. So that is basically the objective of this complete chapter, and this chapter is basically divided into different parts. So we will see each thing separately. So the today lecture is basically focusing on the first part, basic characterization of the signals, basic properties of the signals. So we know that in communication system we both have we have signal and noise. Okay, so basically we have input signal and we have a channel, and from the channel the noise is basically added, right, and we get output. So if we want to characterize the properties of the signal, input signal or output signal, so we can basically, the signal is actually the main component of the communication which contains your information basically. So noise is basically the undesired path which is added. So we can characterize the signal in terms of its DC value. DC value is also called as the average value of the signal. Its RMS value in terms of power, energy, spectrum, magnitude spectrum, and like the power spectral density, energy spectral density, bandwidth of the signal. So we can characterize, okay, the waveforms of the signal and noise in terms of all these things, and we will learn one by one about each path. Okay. So if we talk about the physical realizable waveforms, so basically these are the waveforms which are actually we use in practical, okay, and they can be measured in a laboratory, okay. So these waveforms satisfy these basic conditions. For example, they have non-significant non-zero values, and they could have significant values over a composite frequency domain. Like if you're talking about in frequency domain, the waveform is a continuous function of time, okay. For example, if you draw a cosine signal, it's just going on, okay, it's a continuous function of time. The waveform has a finite peak value. For example, this is a peak value of the sun, so this is a finite value, for example 2 volt or minus 3 volt or like that. So these are the basic properties of the physical waveforms, and the actual physical waveform looks like this one, okay, and eventually it's not like that this waveform is going till infinity, okay. So actually before reaching the infinity, this waveform, actually the actual physical waveform becomes zero. Similarly, negative infinity, it actually becomes zero, okay. But in actual analysis we use the mathematical model of the waveform. So this is the equivalent mathematical model. The first assumption which we make here, that this waveform is continuous, so it's going continuously like this till infinity and minus infinity, okay. So basically mathematical model violates the two basic conditions, the continuity and finite duration. These are the basic property of the physical signal, okay. They are not continuous till infinity, and they don't have they have a finite duration, okay. They exist for a finite duration, but the mathematical models we usually like it's going till infinity and they don't have finite duration. The first characteristics, okay, of the signals we can obtain using the time average operator. Okay, so time average operator usually represented using like these brackets, and we put the parenthesis here and inside of dot. So this is actually representing the time average operator. So we use the time average operator basically for the calculation of the DC value of the signal. Okay, for example, let's say if I want to calculate the DC value of x of t. Okay, so this is my signal. So basically this will be equal to limit t approaches to infinity 1 over t for one time interval, that signal here. Okay, so that will be actually this will give me the DC value of that signal. Okay, and this is a linear operator. Linear operator means, for example, you want to calculate the DC value of two signals. So instead of like first adding them and then getting the applying time average operator, what you can do, you get the average value separately for this signal, average value separately for this signal, and then just add them. Okay, so like solving a signal separately and then just adding them, that is the linearity property of the time average operator. Periodic waveform we know very well. Waveform is a periodic if it is repeating itself after a time period t. For example, this is the time period t, so this waveform is repeating itself after this time period. Okay, mathematically we represent, for example, this is my original waveform, so this is basically its shifted version, right? T minus t naught, and this is its more shifted version, t minus 2 t naught. So in general form we can represent this function as t plus t naught. Okay, so that is this signal omega t is repeating itself after a time period of t naught. So this is called the mathematical form of a periodic waveform. DC value, as I said earlier, average value or DC value of a signal, how we can calculate? By applying the time average operator. That we whatever signal we have, we just put that signal here and we integrate for the one time period. So that will give us the DC value of that signal, okay, or average value of the that signal, or mean value of the that signal. Okay, so for physical waveform we are actually more kind of interested in evaluating the DC value over a finite interval of interest. Okay, for example, let's say this is a kind of a noise signal. So we want to analyze that what is the average value of this signal. For example, let's say from interval t1 to t2. Okay, that how the signal, what is the average value or DC value. DC value means basically the zero frequency component in the spectrum of the that signal. Zero frequency component in the spectrum of that signal. That is the basically DC value or average value of a signal. Okay, so by just taking the integral for the one complete time period, we can calculate the DC value of a signal. And if you want to calculate the power of a signal, so power of a signal is basically the multiplication of the voltage and the current. So we can also calculate the average power. So if you want to calculate the average power, so we can calculate the average voltage for DC voltage and average current. Okay, so we can multiply them so that we can get the DC, the average power of the signal. Okay, so there are examples relevant to this which we will see in the live session. This is example which we will see in the live session. RMS value, so we get one DC value of a signal which we present using this operator. Okay, so this is the DC value of a signal. So if you take the square of that, okay, sorry, square of the signal, and you take its DC value. Okay, you take the square of a signal and then you take its DC value and then you take the square root of that. Okay, so that will give us the root mean square value. Root mean square value or RMS value of a signal. Okay, so basically root mean square value is basically the time average value, okay, or the DC value of a signal. Okay, like it could be like this, like you take the DC value which is basically the time average value of a signal, you take its square and then take the square root of that signal. So that will give us the RMS value of a signal. Okay, so for the power case, we know that power can also be represented as V square over R or I square into R. So if we are putting the DC values or RMS value of the signals here. So basically this will become RMS value square divided by R, or I RMS value square multiplied by R. Okay, or simple V RMS into RMS. We can calculate the power in terms of the RMS values only. So that will give us the RMS value of the power. So the last thing is, if you want to calculate the energy of a signal or power of a signal, so how we can calculate that? So we can classify the signal in terms of the power and energy signal. So if you want to calculate the power of a signal, so just take the magnitude square and then take its average value. That will give us the power of a signal. Okay, that will give us the average normalized power. So basically this is the square root of the normalized average power is the RMS value. So if you have a signal, just take its square, okay, and then take its average value. Average value means take the square and then integrate for the one complete time period and divide it by 1/t. That will give us power. Okay, and the energy is that if you have a signal, take its square and integrate from minus infinity to infinity. Okay, that will give us the energy of that signal. Okay, so we can also classify the signal based on the energy and power properties. So if a signal has finite energy, like greater than 0 and less than infinity, my signal will be an energy signal. And if it has finite power means greater than 0 and less than infinity, my signal will be a power signal. So usually the signal is either a energy signal or a power signals. Okay, and the periodic signals are mostly power signals. Periodic signal is basically always a periodic signal will always be a power signal. Okay, it means it cannot be an energy signal. Okay, if we get a periodic signal, okay, it cannot be an energy signal. So this is the end of this part of the lecture. We will see the relevant example in the live session. We have examples here. Decibel thing, SNR, signal to noise ratio, you know very well about this. So okay, we will see the examples about this again. Okay, and lastly about the phasor representation. Okay, thank you very much for your time.